I want to do another review very briefly of our earth pressures and retaining walls, and we will go into this subject in more depth here. In particular, we are going to develop how we get these values of Ka and Kp. In other words, and all the problems that I've given you this point, I give you a value of Ka, and Kp, but I never say where we get those values from. So we're going to discuss that. And we'll start with remembering that, we have a K naught, we have a Ka, we have a Kp. K naught is the at-rest coefficient. We know the active coefficient, passive coefficient. And they all are defined as sigma h prime divided by sigma v prime. Horizontal effective stress divided by vertical effective stress. So, and the active zones and passive zones. So in other words, we have our wall down here, and this is our active zone, that's our passive zone. Where does the at-rest coefficient come into play? Well, if this wall did not move at all, we're not allowed to move at all, then we would have at-rest pressures on both sides of it. There are situations where we can get at-rest pressures, but most of the time in the retaining wall design process, we're looking at active and passive pressures. So let's look at our problem here. I've got dry sand above the water table, saturated sand below the water table, and we have a water table here, right there, and that's our depths in meters, 0, 4, and 6, and we want to know what is the width of this wall. We're going to use a factor of safety of 1.5 for both sliding and overturning. It's a sand, these are our properties. Friction angle of 34 degrees I've given you. And concrete has a unit weight of 26 kilonewtons per cubic meter. When we choose our depths here, we have 0, 4, and 6. Why 4? Because at 4 is where the water table is. I don't need to go 4 minus and 4 plus because there's no discontinuity at that point. And so all I need is 0, 4, and 6 on the active side, 4 and 6 on the passive side. And, we have our sigma V's, you can all get that. So this is pretty straightforward. Pore pressure from the water table, sigma V minus U gives me sigma V prime. And then I use the active earth pressure coefficient to get sigma H prime. And then sigma H is a sigma H prime plus U. So we get all these columns. And then I do the same thing on the passive side, except I use the passive pressure coefficient. So here are my stresses. I plot them up, and so this is my active, this is my passive, and then at the base I also put my pore pressure. So this is the pressure diagram for overturning. Now remember, what we're assuming is that the wall is pivoting about this point. When it lifts up, I do have my water pressure underneath. And, we're 2 meters below the water table, so it's 2 times 9.8, which is 19.6. So this is the diagram I use for overturning. And I convert these stresses to forces by getting the areas of all of these. So I get, area 1, area 2, area 3, area 4, and area 5. So I convert all of these, by getting those areas, I convert them to forces. Now I have to recognize that this is an unknown value, B, but I just put that into the, I put that into my expression for the A5. In addition, my weight of my wall is going to be also dependent upon this with B. So then when I convert this to forces, I get these forces, and both the weight of the wall and the water pressure have the variable B in it. And I used my factor of safety of 1.5, which is the resisting moment divided by the overturning moment, and I solve for B. And so my resisting moment is dependent, it comes up with B squared, because I take the moment arm for this, or sorry, the moment arm for this one is B over 2, and for the resisting moment and the overturning moment, again, yeah, I've got the 19.6 B times B over 2, so I get 19.6 B times B over 2, so I end up with this expression here to for my factor of safety. That's the 1.5. The 1.5 goes over here. So I can then solve this expression for B, and I get B is equal to 2.41 meters. So that's what's required. I need 2.41 meters of concrete to resist overturning. Now for sliding, notice we have the friction angle. We were given the friction angle, and how do I make use of that? Well, you know, the friction angle gives me the relationship between tau FF and sigma prime FF. And if I look at my diagram, I can see that the tangent of phi prime is going to be tau FF over sigma prime FF. So what happens is that then I solve for tau FF, and I get tau FF is sigma prime FF times the tangent of phi prime. So what do we see? This is shear is similar to my friction force. If you remember the basic expression for friction, F is equal to mu n. Well, F is what? It's parallel to the surface like tau. N is what? It's normal to the surface like sigma prime. So what we see is that this expression here is similar to this expression there. And what do I note? Oh, well, tangent phi prime and mu are similar. So we say that the coefficient of friction at the base of the wall is simply the tangent of phi prime. So previously I'd just given you the coefficient of friction. Well, now we know what it is. It's the tangent of phi prime, which we can get, which we have been getting phi prime. So when we do our load diagram for sliding, well, it looks like the other one, except at the base here, I now have to include my normal forces and my friction force. And the way that we look at the normal force is I break it down into two parts. Well, we have an N prime, which is an effective stress type term, and U, which is the water pressure term. So I want to separate those out for a reason. Because we're separating out the effect of water and the soil particles. Why? Because we separate them because the water has no friction. So I don't associate any frictional resistance with the water. The frictional resistance is only associated with this N prime, the effective stress term, because that is with the soil particles. And so, we can get the friction force as being N prime times tangent of phi prime. Because this is my coefficient of friction, there is my normal force, the normal contact force. And so we get, that is our mu N prime type term. So, and that gives me my frictional resistance. In this particular case, our phi prime was 34 degrees, so the tangent of phi prime, 0.675, that's our coefficient of friction there, 0.675. So when I take my, I have to figure out what is my value of N prime. Well, if I take the sum of the forces in the y direction equals 0, I get that that N prime plus U has got to be 59.6 times B. So in other words, these two equals this, taking the sum of the forces in the y direction equaling 0. And so I can figure, when I get my, when I come up with my factor of safety for sliding, well, what do I know? My resisting force is going to be, what's resisting the sliding? That and that are the only things that are resisting sliding. Well, the 60.6, there it is right there, resisting sliding. But what is this F? Well, we decided that F was the N prime tangent phi prime, comes from up there. And then my sliding forces, these are all my sliding forces right there. So they're the 60 plus 60 plus 27.8. And then that's equal to 1.5 because that's what we specified for our factor of safety. We know that the U is 19.6 times V prime. That's the volume of the stress block at the bottom. So in other words, we're looking back at this we're looking at this. So 19.6 times B times 1 perpendicular to the paper. And so 19.6 times B times 1, that's giving me the volume of the stress block. So my U is 19.6 times B. And that means that when I'm using this little equilibrium equation, that I have, it's N prime plus the 19.6 times B times the 159.6 times B. And that means that N prime is 140 times B. And if N prime, that's my N prime right there. So the 140 times B goes in there. And we get that for my factor of safety. So this 60.6 is that 60.6. And this N prime tangent phi prime becomes this term, the 140B, and the 0.675. And then the denominator adds up to 147.8. I can then solve this expression for B. I get B is equal to 1.70 meters. So for sliding, I only need a B of 1.70. But for overturning, B was 2.41, so what do I have to use? I've got to use the bigger one. It's the 2.41 meters. Okay, so a little bit of review, a little bit of added using our tangent of phi prime for this particular problem. And then, again, the anchored wall, we're using a single anchor right there, and we're assuming that the wall pivots about this particular point, that's a solid anchor, and it pivots about that point, and we're taking into account we have passive on that side, we have active on that side. And then when we do the design, we take the net stresses. In other words, I add the active and add the passive together, and I get something that looks like that to there. But then I, end up, when I add this side to this side, then I get a diagram that looks like this. And so we're going to take moments about this point. This is our net pressure diagram. So we've done this all before. Okay. The next part of this is that we want to be able to calculate out what are Ka and Kp. And we want to look at where they come from. And this is the theory behind it, developed by Rankine. And we're back to our concept that for active pressure, the wall moves away from the soil. So let's think about it again. And we're going to take a point of interest on the wall right there. There's our point of interest. And I'm going to look at the stresses on that point of interest. Well, let's go through the whole process of what takes place at that point of interest, assuming that we can build our wall instantaneously with no movement. So in other words, it's a little bit theoretical, but let's say that I can install my wall and then excavate it, no movement of the wall, and then when I'm done excavating, here for instance, the wall then moves. So a little bit ideal situation, but here's the reason I want to look at it in that manner is that, okay, so as the point sits in the ground and there has been no movement, what are the stresses on that point? Well, the vertical stresses are going to be sigma v prime. The horizontal stresses are going to be k naught sigma v prime. In other words, it's at rest. Nothing has moved. So this is the ideal situation when we can build the wall with absolutely no soil movement, which is not real, but to get us through this this process, you'll get an understanding of why we're making that assumption. So in other words, my Morse circle before any movement takes place is right there. Again, it's very simple to draw. I've got sigma v prime, k naught sigma v prime, I draw the circle. Now what happens as the wall is now moving away? Well, what does that mean? That means that the horizontal stress is dropping at our point of interest, which is right next to the wall. So in other words, we're going to assume that there's not much vertical movement. Yes, the soil here drops a little bit as the wall moves outward, but we're going to ignore that effect because it's not that great. And so we are going to say that that the vertical stress remains constant at our point of interest. There's our point of interest right there. And the horizontal stress reduces. So our horizontal stress gets lower, and so it moves to the left in our figure. And that means our Morse circle changes, And you can see that I drew the various Mohr circles. And what happens, well, it can only drop so much, and it hits the failure envelope, the Mohr envelope. So that it doesn't take a lot of movement to reach that point, interestingly enough. And what we're able to do is then we're able to determine the stresses, the horizontal stresses of a circle that is tangent to the Mohr envelope. And we know the sigma v prime. And by definition, we call this the active earth pressure. And so that's our Ka sigma v prime. And so we can do geometry. We're going to use geometry to determine what that value of Ka is and how does it look. So I'm going to take this circle here. So that's the circle that exists to represent the stresses when the wall has moved out. And I've drawn it down here. So it's tangent to the Mohr envelope. And we have our stresses, so that, in other words, I'm looking at my Mohr circle right here. Well, what is the center of the circle? The center is halfway between sigma v prime and Ka sigma v prime. In other words, there's sigma v prime, there's Ka sigma v prime. So halfway is sigma v prime plus Ka sigma v prime over 2. That is the center of our circle. So that's going to be that point right there. So that means that this distance is sigma v prime plus Ka sigma v prime over 2. And then the radius is going to be the diameter divided by 2. So the diameter is sigma v prime minus Ka sigma v prime. So that's my diameter of this circle. So that's that distance. Dividing that by 2 gives me my radius. So I know the radius and I know the distance to the center. And if I draw this little triangle here, then I know the leg of that triangle and I know the hypotenuse of that triangle. And so I know the leg and I know the hypotenuse. So the sine of phi prime, there's my phi prime. The sine of phi prime is the radius over the hypotenuse. And then I know what I just got the radius. Sigma v prime minus Ka sigma v prime over 2. And I have the hypotenuse, sigma v prime plus Ka sigma v prime over 2. And then I get some cancellation here. So I get that sine phi prime is 1 minus Ka over 1 plus Ka. And if I do some manipulation on that, I can solve for Ka. And I get Ka is equal to tangent squared of 45 minus phi prime over 2. And I'd like you to memorize this Ka. So in other words, what have we got here? If I know my friction angle, I know my Ka. Well, we did a lot of tests. Oops. And we've evaluated phi prime. So for our soils, and so for our sand. Now, this is a sand, obviously, because it's my failure envelope goes to the origin. Sand or gravel. Given that we can, given that phi prime, we can get our Ka calculated very simply. I want to make one other observation, and that is that now that we've derived this, for K naught, now this is not theoretical. But as an estimate of K naught, people use 1 minus the sine of phi prime. So there's no derivation that goes with that exactly. It's just approximately what people have observed for K naught. So I want you to know that value as well. So 1 minus, I should say, memorize both of those values. It's a good estimate of what K naught is. K naught's a little bit harder to determine. But, okay, so what I want you to know from this is if we know phi prime, we know Ka. Tangent squared 45 minus phi prime over 2. We can do something similar for the passive side. So here's my passive zone over here. And here's my point of interest right there. And again, we start out initially with the same stresses, sigma v prime and K naught sigma v prime. But what happens when the wall moves in this direction, what happens? Well, the horizontal stress increases, not decreases. So this horizontal stress then does what? It moves in this direction and keeps moving until when? Until I get a circle that again is tangent to the Moore envelope. But now I'm on the other side. I'm on the right side of my diagram. And so I'm going to take this big circle here, and that is this circle here, and do the same sort of math in that I have my sigma v prime, and then I have my Kp sigma v prime. We call that the passive stress, passive pressure. And so it's Kp sigma v prime, and how do I get that? Well, where's again, I'm going to get the radius as, well, the center is sigma v prime plus Kp sigma v prime over 2. In other words, that splits those values. And then the radius is going to be the diameter divided by 2. So the diameter is Kp sigma v prime minus sigma v prime. Divide that by 2, that gives me the radius. So again, I have my center there. I have my radius there. And again, the sine of phi prime is going to be the leg over the hypotenuse. And so radius over hypotenuse. And again, I get cancellation. And so I get that the sine of phi prime is Kp minus 1 over Kp plus 1. I solve for Kp. And what do I get? I get Kp is now tangent squared 45 plus phi prime over 2. So the only difference is the plus sign. So in other words, so let's go back through this. The Kp is tangent squared 45 plus phi prime over 2. Ka is tangent squared 45 minus phi prime over 2. So it's easy to remember both of these. You just remember that Kp is plus, Ka is minus. So tangent squared 45 plus or minus phi prime over 2 gives us our Kp and Ka values. Okay, I'm going to stop there.